Welcome back. Problem 12-39. So this problem is taken from chapter number 12, that is deflection of beam and shaft, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the maximum deflection of the cantilever beam. The beam is made of material having E is 200 gigapascal and I is 65 into 10 to the power 6 millimeter power 4. So you can see this is a cantilever beam that is fixed at point A, and at this end we have 15 kilonewton load, and from point A till length of 1.5 meter there is a uniformly increasing load or triangular load that is 30 kilonewton per meter. So due to this load the beam will deflect like this. So we have to find the maximum deflection of the cantilever beam, that will be at this end, Vmax. Okay, so let's start with the solution. So first step is that if we remove this support, fixed support at point A, so you will be having a reaction force. Let this force is Ra, and there will be a moment which is represented as Ma, and you can see that this is a triangular load. So if you want to convert it into point load, so this will be 1/2 into 30 multiplied by the length over which it acts, that is 1.5. Clear? And this will act at a distance of L by 3. So L is here 1.5, so 1.5 divided by 3 will give you 0.5 meter, and this remaining distance will be 1 meter. Now we will apply equation of equilibrium for finding this Ra and Ma. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So one force is Ra, the second one is this one, and third one is this one. Their sum must be equal to 0. So Ra is upward, so we will write Ra plus, the other one is downward, so 1/2 into 30 into 1.5, and the third one is minus 15 is also downward, so their sum must be equal to 0. So from here we will have Ra minus 22.5 minus 15 will be equal to 0, and this Ra will be equal to 37.5 kilonewton. Okay, so this is the value of Ra. You will find moment. So for moment we will apply equation sum of all moment about point A is equal to 0, taking the counterclockwise moment as positive. So about this point A, this Ra is passing through this point, so it is not producing moment. So first moment is this one, which is the reaction moment, that is Ma, and that is counterclockwise, so it will be positive. So Ma, the second moment will be produced due to this force into perpendicular distance is 1 meter, and this is producing clockwise, so it will be negative. So I will write minus 1/2 into 30 into 1.5 multiplied by perpendicular distance is 1. The other moment that is produced due to this 15 into perpendicular distance is this one, which is 3 meter, and this is also producing clockwise, so it will be negative. So I will write minus 15 into 3 is equal to 0. So Ma minus 22.5 minus 45 is equal to 0. So from here you will get moment, reaction moment at point A comes out to be 67.5 kilonewton into meter. So you having this reaction moment. Now what we are going to find, we are going to find out the maximum deflection, for which we need the equation of elastic curve. So equation of elastic curve can be found by using this formula, EI into d square V over dx square is equal to moment. So we will find the moment equation for this beam, and you can see that we have this table, and in row number 4 you can see the loading slope. In 1 you can see the moment, in 2 you can see the loading, that is point load, and in 3 you have distributed load. So what we, if I draw the free body diagram, Okay, so if I draw the free body diagram of this beam, so it will be like this, where you have Ra that is equal to 37.5 kilonewton. You have moment which is 67.5 kilonewton into meter. Okay, now you can see that here you have a load, uniformly increasing load, and this is up till this length. And from this table you can see this uniformly distributed load starts from here till the end. Clear? And this is at a distance from of A from this, x start from this. So what we will do is that we will convert, we have we we have this load, uniformly increasing load till the mid. Okay, let this is the mid. So we have uniformly increasing load like this, which is 330 kilonewton per meter. So what we will do is that we will add, this is at a distance of 1.5 meter from this side. So 1.5 meter, and the remaining is also 1.5. Okay, so just remember this is 1.5. So if we move it till the end, because in table it is till the end, so this will be the load. Now you can see this load will be like this one. And the amplitude of load at this point, we have a load of 30 kilonewton per meter, but here at this point the load will be 60 kilonewton per meter, because this is of length of 1.5 meter. So same is the case if you look at this, so we can divide it like this. So this is 30 kilonewton per meter. So same, if to, in order to cancel the effect, so we will add the same 30 kilonewton that will be acting upward, and now this remaining portion that will be also upward. So this is 30 kilonewton per meter, and this will be also at this point we will also have 30 kilonewton per meter, and the sum of this plus this will be 60, which will cancel the effect. Now at this end we also have a point load of 15 kilonewton, so I will choose another color. At this end we have 15 kilonewton. Now we will use this table in order to find the equation of movement. So I will write it. You can see first we will take this RA, R37.5, that is point load. So you will consider this equation, movement equation. So M is P into X minus A. So P will be 37.5 into X minus. Now here A is equal to 0, because it will start from the, it will act from this starting point. So X minus 0 power 1. Now we'll take this movement, which is this one, and that is the movement equation will be this one. Okay, so since this movement is clockwise, so this is positive, so here the movement is counterclockwise, so it will be negative. So minus 67.5 into X minus A is also again 0, because the movement is acting over here. Clear? So A will be equal to 0. So X minus 0 power 0. Now we will take this uniformly increasing load till this point, and this is triangular load. So for triangular load we will choose this formula. What is small m? So small m is slope, and slope of this triangular load will be equal to perpendicular, this perpendicular over this base. So perpendicular is 60 and base is total length is 3. So I will write m is equal to 60 divided by 3, which is equal to 20. So m is equal to 20. So I will write this moment equation, and this load is downward and this is upward. So this will be minus m by 6. So m is 20. So 20 divided by 6 into x minus 0. Why 0? Because this load start from this x is equal to 0. So a is equal to 0 over here. Okay. Now we have this load which is 30, and this load you can see is uniformly distributed load or length of 1.5 meter. So this is the equation of uniformly distributed load, and the load is upward, so it will be plus W naught, which is 30 divided by 2 into x minus. Now this load start from here, so this A is equal to 1.5. So x minus 1.5 power 2. And we will left with the last one, which is this one, this uniformly increasing load. And for a uniformly increasing load, we again will move toward this equation. So that is load is upward, so it will be plus m. So m here, m2 will be equal to this perpendicular, which is 30, and base is 1.5, which is also give you 20. So it will be equal to 20 divided by 6 into x minus 1.5, because it is here a is equal to 1.5 power 3. Okay, so there is 3 over here. Now if you further simplify it, so you will get moment will be equal to 37.5 into x minus 67.5. X power 0 is 1, so minus 20 divided by 6 will be 10 by 3. So 10 divided by 3 into x cube, and this term will be also 10 by plus 10 by 3 into x minus 1.5 times cube, and this term will be plus 15 into x minus 1.5 times square. So this is your moment equation. So put it in this formula. So you will get EI into d square v over dx square will be equal to 37.5 x minus 67.5 minus 10 over 3 x cube plus 10 by 3 into x minus 1.5 cube plus 15 into x minus 1.5 whole square. So what we will do is we will integrate this equation, integrate it. So you will get EI into dv over dx will be equal to 37.5 x square divided by 2 minus 67.5 x minus 10 into x power 4 divided by 4 into 3, which is 12, plus 10 by 10 into x minus 1.5 power 4 divided by 4 into 3, 12, plus 15 into x minus 1.5 whole cube divided by 3 plus c1x. And if you further simplify, it will be equal to 18.75 x square minus 67.5 x minus 5 by 6 x power 4 plus 5 by 6 x minus 1.5 power 4 plus 5 into x minus 1.5 power cube plus c1. Sorry, it is c1, not c1x. So let this is your equation number 1. So what we will do is that since we are interested to find out the equation of elastic curve, so integrate equation number 1, integrate equation 1. So when you integrate it, you will get EI into V, which is deflection, is equal to 18.75 x cube divided by 3 plus minus 67.5 x square divided by 2 minus 5 into x power 5 divided by 6 into 5, which is 30, plus 5 into x minus 1.5 power 5 divided by 6 into 5 is 30, plus 5 into x minus 1.5 power 4 divided by 4 plus C1x plus C2. And if you further simplify it, you will get 66.25 x cube minus 33.75 x square minus 1 over 6 x power 5 plus 1 over 6 into x minus 1.5 power 5 plus 5 by 4 into x minus 1.5 power 4 plus C1x plus C2. So this is your equation number 2, and that is equal to EI into V. Now C1 and C2 are unknown constant of integration, so we can find by using boundary conditions for finding C1 and C2. So first boundary condition is that at x is equal to 0, we have slope dv over dx will be equal to 0. So let me show you over here. I have already told you in the start that due to this, the beam will deflect like this. Clear? So here at x is equal to 0, we have slope which is dv over dx is equal to 0, because this will be a straight line, so tangent to this straight line will give you slope. So what we will do is we will put in equation 1. So when you put it in equation 1, so dv over dx is equal to 0, this term will be equal to 0, x is 0, this term will be 0, this term will be 0, this term will be 0, and 0 minus 1.5 is minus 1.5 power 4. So anything inside Macaulay bracket which is negative will be considered as 0. So this will be 0 and this will be also 0. It means that C1 is equal to 0. So I will write, you will get C1 is equal to 0. Now the second boundary condition is that at x is equal to 0, we have deflection V is equal to 0. So here you can see this end is fixed support. So at x is equal to 0, we have deflection is equal to 0. So we will put in equation 2. So this is the equation number 2. So this term will be 0, x is 0, so this term will be 0, this term will be 0, this term will be 0, and 0 minus 1.5 is minus 1.5 power 5, and this is inside the Macaulay bracket, so any negative term inside the Macaulay bracket will be 0. So this will be 0 and C1 into x is 0, so it means C2 is also 0. So from here you will get, you can just put it, I am skipping it so that to save the space. So C1 and C2 is equal to 0. So what we will do is that put C1 and C2 in equation number 2, that is about deflection. So we get EI into V is equal to 6.25 x cube minus 33.75 x square minus 1 over 6 x power 5 plus 1 over 6 into x minus 1.5 power 5 plus 5 over 4 into x minus 1.5 power 4. C1 and C2 are 0, so this will be the equation. And if you divide EI on both sides, so you will get V is equal to 1 over EI into 6.25 x cube minus 33.75 x square minus 1 over 6 x power 5 plus 1 over 6 into x minus 1.5 power 5 plus 5 over 4 into x minus 1.5 power 4, and this is the required equation of elastic curve. Now in question we have been asked to find the maximum deflection, so maximum deflection will occur at the free end. This is the maximum deflection, this is maximum deflection, and this occur at x is equal to 3 meter. So put x is equal to 3 meter in this equation, so you will get Vmax will be equal to 1 over EI into 6.25 3 cube minus 33.7 into 3 square minus 1 over 6 3 power 5 plus 1 over 6 into 3 minus 1.5 power 5 plus 5 over 4 into x, which is 3 minus 1.5 power 4. So again, when you solve this, you will get Vmax will be equal to minus 167.91 over EI. Okay. So now you have the value of E and I as well, that is given 200 gigapascal and I 65 into 10 raised to the power 6. So put it minus 167.91. This will be, the unit will be in kilonewton, so I will multiply 10 raised to the power 3 because this all the loads were in kilonewton. Okay. So divide by E, which is 200 gigapascal, 200 into 10 raised to the power 9. And I is 65 into 10 raised to the power minus 6. This is minus 6. Okay, this is plus 6. So that is I is 65 into 10 raised to the power 6. And when you convert it into meter, so meter power 4. So there will be 10 raised to the power minus 12. Meter power 4. So this will be 65 into 10 raised to the power minus 6 meter power 4. So I will write 65 into 10 raised to the power minus 6, and when you calculate it, you will get Vmax will be equal to minus 0.01292 meter, or you can say Vmax is equal to minus 12.9 millimeter, or Vmax is equal to 12.9 millimeter, and that is downward. So this is the maximum deflection of the beam for the given loading. And that was all about this problem 12-39. I hope you have enjoyed this video. I will prefer you to now practice it by your own so that you have a clear understanding. Again, those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.